Here we go. Okay, we already read this part. Feature degradation. I'm also curious how they decide which features to degrade. It's kind of a difficult decision, I would imagine. Like, how do you tell somebody that their feature is one that is going to be turned off if there's a serious problem? Or maybe it is automated to some degree, or they don't have a choice. I'm curious also which products this is for. Is it for all Meta products, or is it just for a subset of them? And if it's only for a subset, how easy is it to extend it to a wider set of products? So cool. So they can disable less critical features in order to reduce resource demand. And they do this using what they call feature knobs. Oh, that's cool. And they also use the knobs not just under load, not in emergency situations, but also to understand how many resources a feature takes up. Okay, and then they say they've used Defcon to improve global availability in the face of worldwide demand surges. So I'm curious how much have they increased availability? So now let's look at the introduction. They power human life, modern human life. Alibaba, Amazon, Google, Meta, Microsoft, and Netflix. I'm not sure that is that Apple's not in there. So this is Magna. This is not Fang. This also has an N in it, so it's not Magma. And also, Alibaba is replaced by Apple, which is funny. So I'm not sure what is the acronym for this group of companies. Magna. Anyways. Okay. Cool. They talk about features. And there are different features. And site operators deploy resources to service features, and they do that around the world. And they must make sure that the workload to power those products does not exceed the amount of resources that you need to, the amount of resources that you have, rather. So planning resources is also very closely related to the Flux paper. So basically the motivation is, how do you degrade resources / this is also called load shedding. If you search like the SRE load shedding book or SRE book. Load shedding. Managing load and addressing cascading failures. So load shedding is a common idea. Cool. What about this one? This one seems like maybe not as relevant. But managing load, I think, is still relevant to some degree. Okay, so you have to plan for how you allocate resources. Cool. So this is interesting. They're saying, oh, there are errors and inaccuracy in models and forecasts, which is also alluded to by the Flux paper. Flux paper So at the end of the day, the people that use internet services care about availability. Can they use the product that they want to use when they want to use it? So, yes, I think that's true. There's another quality that we know that users care about, which is latency. And so I'm curious, obviously availability, or maybe not obviously, availability is more serious than latency. But if people can use a product and it's slow, it could be just as bad as not having the product at all. So it's interesting that they don't necessarily make that distinction. And that could also like imagine that you had few resources then available and you couldn't actually have all the servers that you wanted to power the product. That means that requests might need to wait some period of time. That would introduce latency and users would be annoyed. I think there's some quote which is my favorite feature. My favorite feature is fast. It's fast. It's formally set by a Google engineer. Yeah, speed is a feature. So, the Google Gospel of Speed. Who wrote this? Urs. Okay. Anyways. So then they ask a bunch of questions. What happens when things do not go according to plan? Can we achieve high product availability without sacrificing additional resources? Can we be more efficient for rare but inevitable partial outages? Cool. So a bunch of motivation. And then, okay, cool. They have an example. Oh, this is one of the things I actually really enjoy about the meta papers is they're very often based on production experiences. Specifically, their systems papers. So mega instructions per second. Okay. So they're talking about fail slow behavior. And they're talking about there is a spike in usage around peak. So this is what we're looking at right here. There's a spike in usage around peak. And they also talk about fail slow, which is a I'm wondering if they're saying fail slow. So fail slow means, or generally means, that there is hardware that stops working, but in a non-obvious way. So an example would be a previous paper review on microlearner.com was around Perseus. Fail slow. It was around Perseus, which is a system for detecting fail slow conditions in storage, essentially. So I'm wondering, I wonder if they are saying that if the system gets overloaded, it could push the hardware into conditions where it is more likely to fail slow over the long term. That is my interpretation of what they're saying. Overload makes sense. Also, this is very closely related to another paper about metastable failures, which was written by a group of authors. Metastable failures in the wild, which was written by a group of authors who looked at systems that essentially get pushed into overload and then as a result have, or maybe they are using, I think this is relevant. They get pushed into overload and then essentially they they get put into a vicious cycle where, okay, they can't serve requests because they're overloaded, and then because they can't serve requests, then there is some, this is also very similar to the idea of cascading failure. So they can't serve requests, and so as a result, requests fail, and then because the requests fail, the clients retry them, and then you have more requests on top. So there could be this cascading failure because of some problem with capacity. And I think the metastable paper also talks about how there could be problems with capacity, like if there's a subtle performance regression, for example, in a service, you might think that you have enough capacity, but then once the system is pushed to its limits, you actually discover, oh, the actual capacity is less than the predicted capacity. So very interesting connection to metastable systems. Cool. So that's cool. That's really cool. Yep. Not all product features provide equal value. Many features can be safely turned off. Okay, so now we're talking about contributions. So they characterize the overload problem in solution space, apply a rigorous data scientific methodology to analyze knob behavior, and describe a real-world at-scale testing methodology. So, okay. Okay, so Graceful feature degradation. Very cool idea, and they're doing it at scale, and they have a bunch of production data. That's the takeaway, my takeaway. Okay, background. Data center. Let's see how we're doing. See how we're doing. We got 2 viewers, nice. Okay, we got a few more viewers, nice. Data center capacity management, the overload problem, related work, Graceful feature degradation, Defcon. Okay. I'm very interested in how how they have the client side knobs. That's very interesting. knob. Very cool. This is very cool. Client-side knobs. Knob actuator service. Then they have valuation of the system, measurement, methodology. We got individual product tests. Combined product tests. Very cool. They work closely with SREs. Lessons learned. Conclusion. Okay, let's read the conclusion. Cool. Advanced, reliable, and available distributed system design. Okay, that seems pretty reasonable. I'm looking forward to diving a bit more into the actual implementation. Let's see what some of the papers that they represent, or papers that they reference. This is interesting. From SRECon, it's another of the Usenix conferences, as you can see here. Very cool. They even referenced one of the metastable They even referenced the metastable paper. So that's exactly what I was just talking about. Very cool. Not planned. I promise that I haven't read this paper. Graceful degradation of search quality. Oh, they even also reference graceful degradation from S3. So this is right, and they also reference a fail slow at scale, the fail slow at scale paper that I wasn't talking about that specific one, but the Perseus. This is, I think, one of the canonical papers about fail slow at scale. So I've read this. Okay. Another metastable fail. This is the metastable failures in the wild. This is the metastable paper that I wrote about, and this they refer to each other, but they're both written by authors that I was familiar with. Alexei Trapko also runs an amazing reading group that's on Wednesdays on Eastern Standard Time. So highly recommend attending a Trapko. Let's see if I can find it and send it to the chat. There it is. More viewers. Hello internet. Metastable paper. Okay. So anyways, back to what we were doing. So yes, I've read this one. Canopy. That sounds very interesting. Brownout. building more robust cloud applications. Scaling your cache at Facebook. I've written about this on my blog. Oh, availability knob. Flexible user-defined availability in the cloud. I wonder if any of these people ended up working on this paper. David Watzlaw and Mohammed Sharat. Doesn't look like it. Maelstrom. Maelstrom is also mentioned by the Flux paper. They talk about hack. What else? Load shedding. Specification. Interesting. Okay, so there are a few papers that I want that they reference that I want to read, or resources rather. And then let's see. Metastable failures. Canopy sounds pretty interesting. Maelstrom. And then what else is there? I think that's it that I hadn't read that I was interested in, or that caught my eye, rather. Generally, if I see a paper a few times, I feel like I should probably read it if I'm going down some rabbit hole. So okay, so I think that's it. Let's see how we're doing on time. We got a few viewers, nice. Let's test how the audio is. If I'm going down some rabbit hole. So okay, so I think that's it. Let's see how we're doing. Okay, so let's read the rest of the paper now. Carefully read the title, the abstract introduction. Yep. I answered the 5 C's, I think. The paper's contribution is that it talks about a framework for implementing rather, feature degradation at scale. And with some production learnings. And we will get to the how does the paper. Basically, lessons from production, tests that they're able to run, simulations. Yeah, sounds right. Okay. So cool. So now let's do the background. Start the timer. Okay. Capacity engineers rely on 2 inputs in order to make data center capacity planning decisions: workload resource demand and server resource supply. So there's a clear connection to Flux here, which is the paper that I read around Facebook or Meta's capacity management. Okay. So they normalize They normalize resources to a common standard called RRUs. I think that's pretty common across cloud providers. Like there are vCPUs on other cloud providers. So that makes sense. They have some, standardization of resources. Whoa, chart trending up. More viewers. Welcome to the stream. Cool. Cool. So they're talking about overload induced and fail slow. So normally they would be able to grow their systems at some large, based on growth, but maybe that isn't possible in the future just because there's, you have to have some lead time. If you're building data centers, you need to have more resources that are coming online. And then also data center problems can change whether you have resources. And then we also know from the Flux paper that sometimes if there's manual resource planning, that maybe the service that you have is more likely to run in a specific data center, which has a specific mix of, or specific region rather, a specific region that has a specific mix of resources. And so maybe your region, the region that your product normally runs in, is having problems. We know this from Flux paper. Let's see if I can find it. They show this here someplace. Here it is, yeah. So there's some regional hardware type distribution. So if your system, for example, needs a lot of compute and it's in region A, and region A is having a problem, then maybe it has to go to region F, which doesn't have any compute. And then you're in a whole load of trouble. So that's cool. There's a clear connection to Flux. Can an LLM do that? That's my question. Can an LLM make connections between papers? I don't know. Okay. So, what do you do? They talk about a table of what to do when there's overload. Table 1. And they're talking about, let's read through this and then look at the table. Okay. They reference metastable failures explicitly. Very cool. Very cool. Metastable. Okay, so what are some potential solutions? I really like that they laid it out this way. This is like the way that a tech lead would lay out solutions to the problem. So they are grading approaches based on resources, engineering effort, and user impact. Challenges. For example, COVID made projections totally wrong. I wonder what they did during this time period. Okay, so they're talking about some of the options. So the options are, okay, do nothing. Overload happens. You're not doing anything about it, but users are significantly impacted. You could over provision. That means you give more resources, but then you're spending a lot of extra money. You don't have to have any engineers do it, and maybe users are never even impacted, but you're spending a lot of money. Dropping requests. This is like load shedding. Means that you discard requests, but that could also that certainly impacts users because you're dropping requests, so they'll probably notice that the requests that they're sending are not reaching the servers. And I would say honestly, even that could even lead. You're not really sure what the impact would be, and maybe you still end up in a bad state because maybe if you're dropping requests, then the clients, like if you had the Facebook application, the clients aren't well behaved, and so they're like, my networking requests for the Facebook feed are failing. I'm just going to keep retrying until they succeed, which maybe would make the problem even worse. So I think dropping requests seems kind of dangerous, but maybe necessary. And then you change some servers to figure out when to drop requests, which seems also, yes, very complicated. Like how do microservices even decide whether to drop requests? Is it custom per microservice? I know that Facebook/Meta have systems like Tau, the graph store, and is that, maybe that has some custom load shedding that you'd have to implement. I don't know. So yes. Then they talk about, degrading product features. This is what they chose to do. And maybe there's some other pros of actually being able to degrade product features. So, okay, cool. I'm curious. Yeah, so they qualify what the actual engineering effort is. So reasoning is that you can user impact actually potentially get some pros out of it, but there's engineering effort. I would say there's probably also, it seems like there would also be organizational effort. And I think we'll learn about how they actually implement this, but trying to imagine that you're telling some group that their feature is actually low priority seems difficult. So anyways, and then they have figure 2. Cool. So they talk about some of the related work. They talk about how it's been in other systems. Okay. Product level, feature-centric approach. Yeah, load shedding. They're talking about that. So you can drop a proportion of load by dropping request traffic when a server approaches overload. Relaxation matrix. So they adopt the knob nomenclature from previous research. knob control plane into configuration management. Okay. Okay, so they talk about a variety of specific of related work, but probably the most closely related is the availability knob. Okay, so okay. For example, the number of results can be considered as an adjustable feature for a search product. Interesting. Okay. Okay. So now they talk about how Defcon actually works. Let's see how we're doing on time. Got 47 minutes. Okay. So when I'm reading a paper like this, I like to break down the individual components. So for example, when there's a system diagram, I will just make a bulleted list that has everything that's in the system diagram and then try to explain each of them. So for example, you have the knob actuator service. This is actually, I think, the sections perfectly map. There's a degradation framework. I think we'll probably go a bit deeper on this, and then there's a policy. Okay, so things don't perfectly map, but yeah. I'm also curious how many of the features are integrated with this knob framework. Okay. Okay. So there's a framework. So yeah, so what they're talking about is oftentimes there are flags in servers. I think this is like, what is it? Stateless server manifesto. Not serverless. It's like 13 manifesto configuration. 12-factor app. That's what I'm referring to. The 12-factor app. So they talk about config. Store config in the environment. So the 12-factor app. I'm not sure. Martin Fowler. So yeah, they talk about, it's related to some of those ideas. So they have there's basically a flag. So say for example, foo feature, and you want to turn foo feature on in server A and not in a deployment of server A and not of a deployment of server B, rather than changing the code in server A and server B. So like rather than changing an if statement or like literally changing the code, recompiling and deploying, you will have some code that says, if foo flag is turned on, run this. If foo flag is turned off, run this. So that is something that a lot of servers have. They're saying that isn't what knobs are like, because oftentimes those flags require a binary restart. So there's some configuration management system that is outside of the flags that they reference. Okay. So they have two types of flags, server side and client side. Adjust knobs in seconds without propagation delays. And then you have the client side knobs. So this is actually implemented on device. Yeah, okay. So push changes to the client. So the client side knobs, this makes sense. Like you can imagine that there's a flow of traffic, for example, and that traffic, if you don't tell the Facebook app to stop sending the requests and you just drop the requests once they reach the server, then the Facebook app will be unhappy. But what if you controlled the Facebook app so that it didn't send the request at all? Or it turned off some feature. So that seems ideal, or that seems better. But there are cons, including how do you inform the application that it needs to make some change to a knob? Push change to client. And then you have mobile configuration pull, which is client pulls state from server on a recurring basis. Cool. And then they actually have this third way, or a related way, which is in an emergency. That would make sense. For example, if fetching the configuration through the normal route was broken, then how do you restore the normal behavior of the application? So you need some emergency backup. Okay, then there are actual definitions of the knobs. Sorry, two types of knobs. But yeah, cons of client side is maybe you have more fine-grained configuration, but takes longer. Then there's the actual knob configuration or definition to do listing one. Represents things about the knob in code. For example, the on-call team, there's some namespacing, whether the knob is enabled. Then it looks like they also have some level. So what happens how about if you turn this off? And then there is a usage of the knob definition, and then usage of the knob. Knob is a fun word. If statements based on whether the knob is on. I'm interested, like, what is the integration with the other systems that Meta has? I'm aware of Meta having a system that is for experimentation. So does this integrate with the Meta standard experimentation system? It's not clear to me. So that is, I'm not sure if that will be answered in here. And they talk about how to use knobs, Testing 2. Okay. Okay. So knobs are defined at product. So there's some abstraction over the individual knobs. Looks like. Oh, they actually do talk about this. Next paragraph, they talk about experiments. Okay. So, okay. Aha. This is exactly what I was asking about. Okay. This is very interesting. A lot of references. I wonder how many usages of the word knob are in here. 193 usages of the word knob. This also integrates with the other features. Okay. Okay. So they have a service for storing knobs, which may be index on the knobs, and it's a MySQL database. Not super fancy. I assume it's not super large as well. But I could be wrong. Okay. Interesting. So on-callers can also use the make changes. Okay. Okay. So they do A/B tests. Okay. So they have small scale tests, 2 types of tests. Well, and then we'll do, we're going to read the rest of this section, and then we'll get to evaluation, and then, we'll read the rest of the 3-point whatever series, and then we'll go back and recap. So small scale tests. So they have, the goal of the testing framework is gather data about what manipulating knobs does. So small scale tests. These small scale tests. Typo in the paper. Validating. Should I use a new color if I find typos in a paper? What's using TRU? Oh, transitive resource utilization. Okay. different groups have the knobs turned off in different permutations. Yeah, one of the things I think this is a very interesting paper. One of the things I'm not a huge fan of is that they talk about the levels later. And they give definitions for the levels later after they're already deep in explaining what it is. Also, they are using acronyms. My technical writing teacher told me never use an acronym if you haven't defined what it is previously in the paper. And I think the first reference to this acronym is later in the paper. Is it used previously? I don't think so. Match case. Yeah. So the first reference to this acronym is after they've already used it for the first time. So my technical writing teacher said don't do that. Okay. Then they run server-based tests. Huh. Okay. Then they have large-scale tests. Quarterly 100% of user tests. Okay, so they have per individual and across meta tests. Okay. Product teams are responsible. I'm curious how the product teams became responsible for this. So this is actually be a really good Okay, so they have different levels of different degradation. L4, L1 through L4. L1 is most serious. Okay. Cool. L3 is used for handling overload situations resulting from relatively small scale spikes. Okay. Cool. For setting target level savings, portfolio knobs. And then they talk about how emergency The thing that's also very cool about this is that you could imagine that that there's some feature that ships some bad set of changes, and that feature needs to be turned off. This allows you to do that, and or also just degrade part of the feature if necessary. So I think that's very neat. Okay. Great. So there's some policy, something that emergency responders do. Okay, so now how do they evaluate it? And they use it across Facebook, Instagram, Messenger. Okay, so how do they measure? How are we doing on time? So they have real-time monitoring system, resource utilization, transitive resource, user behavior, okay, so the real-time measurement looks at hardware, measured using so they have some source of truth for available resources, and they have it based on load tests. Sounds very similar to Flux. Okay, so they have the transitive. They use distributed tracing, which again seems similar to Flux. And then they look to see how users behave during a test. Okay, so then they have different data sources, and this looks at like apparently what the hardware thinks is happening. Okay. So then they have these other measurements, which are on a product level or feature level. Okay. Okay, so let's go back. Using these systems, we measure two system level metrics during testing: the global savings and resource utilization on the product, service, or feature under test using RMS. Okay. I think we'll understand more. later. We'll understand more later. Welcome, you people, to the stream. Okay. Oh, that's cool. So they have forecast and a backcast. Okay. Facebook also has a thing called profit. Facebook model for time series forecasting. So, yeah. So that's relevant. And then okay, great. So they basically, that makes sense. They do some forecasting because obviously if the signal is turned off, or if the feature is turned off, then they don't have a, is that correct? Yeah. They basically just want to know what the saving is. That's the takeaway, I think, from this section. Okay. Then they perform A/B tests. Okay. Okay. So for basically for different product areas, higher levels of degradation save more resources. Make sense? Okay, let's table 2. So, okay. All the knobs. Okay, so we observe the degradation generally leads to relatively small user interface interaction changes. So they also say summary is that they small impact to user interactions, but big win. But they're big wins in not having the site be overloaded. Okay. Okay. Okay, so then they have combined product tests. How are we doing on time? Okay, got 17 minutes left. Okay. Okay, so then their shared services. Their shared services that they want to how performance of want to know that's also very closely related to the scaling Memcache at Facebook paper. Okay. Enabling Defcon across these led to compounding resource reduction from Memcache. Oh, this is super cool. Super cool. They have user reports. Very interesting. Very cool. Okay. Okay. Example of transitive resource change. Okay. Really like this paper. Really like this paper. Very cool. Learning from production. Okay. So next, explore in more detail how transitive savings affect dependent services. Okay, so crucially, note that knobs for the feed product were only enabled during the first half of the annotated test range. And while other products participate in this test, using TRU, we were able to observe the resource changes for only a single source of requests. Okay. Which one are we looking at? What are we looking at? Oh, they even talk about tau. Okay, wait, I think this is figure 9. And TRU stands for transitive resource utilization. Okay, so they're basically saying resources used because of a specific product. Okay. 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 Okay, so this is basically saying downstream services with no knobs. I think I understand what they're saying. Downstream services with no knobs can still benefit. For example, tau. Tau doesn't get overloaded as well. Okay. Figure 13. This is that's cool. Very cool. That's very cool. You think that they would also know this without having to run tests, but I guess not. Like they could run this. I guess they wouldn't necessarily know the fine-grained nature of what turning a knob off, the fine-grained nature of how a specific part of the product impacts resource usage. That's interesting. But I wonder if some of this capability could be done with the tracing framework. So or maybe it is done with the tracing framework. And then what else? So they also get breakdowns of okay. And then there's also interdependence between products. For example, Instagram uses Facebook. Okay, outage simulation testing. This is cool. This idea of trying to force failure is something that is common among SRE teams. Okay. Cool. So they test by redirecting traffic, forcing overload, and then using the knobs. Figures 17 through 20. And it's also general. They claim it's also it's very interesting because they have, they're talking about turning on knobs changes 3.2% for feed resource usage, 2% for tau, 8% for memcache, and 6% for graph source. So it's like, oh, it turns out this product actually uses this mix of resources. Okay, and then they talk about some large-scale outages. But let's first look at this. Okay. I think this is actually, figure 17 through 20 are actually fairly similar. Okay, so 4.6. So actually, Meta's equivalent of SREs are called production engineers. Technically different. I also think the production engineers at Meta are embedded, or I've at least heard that they are embedded with the specific product team. So you'll have like a team of developers working on a feature, and then they have a production engineer, which is a bit of a different model than other SRE teams, but seems interesting. And the developers are able to work very closely with somebody who is an expert in production, but also has its cons. So, including maybe all the on-call load, or predominantly all of the on-call load is on that one production engineer. I'm not sure if they still do it that way. So, cool. So during incident, you have an incident manager who decides what degradation policy to apply. Incident manager. Okay. Cool. So they actually went in the incident. They used L3 knobs. Instead of L2. Cool. They have mock fire drills. Common technique for training SREs. Different teams call them different things. In some sense, being on call for a large service that a lot of people depend on is a bit stressful. So it's good to have some practice. I've also heard them called other things. Okay. So what is the graph for this? Where did they they don't have a graph for it. Okay, that's fine. They have a lot of other graphs. So lessons learned. Very interesting to see. Okay, yes. Focus on the user. Focus on the user. Focus on user impact to define knobs. Okay. Leveraging. So graceful degradation doesn't come for free, basically. That's what they're saying. You need to train people on how to use it. I'd be curious how they actually got to this system. In terms of how did they get product to agree? Mm-hmm. Oh, interesting. Interesting. We're going to organize monthly Defcon meetings per product to showcase each team's work to their organizational leader. Very cool. Very smart. Very smart. I've seen similar practices for driving other types of agreement in organization. Reporting ongoing reporting is a good practice to have. Cool. Defcon champions. There needs to be buy-in. Yeah. Yeah, this is interesting. I mean, you'd wonder, like, could you even? You can imagine that there's some project related to the natural extension of this project is to try to automatically come up with what the knobs are. Like, oh, you have data on what users are touching, and that is this feature. That would be really interesting, actually. Because otherwise you have a bunch of people manually changing knobs. Okay. So they also have some independent system. The system honestly doesn't seem super complex. Like, it's a MySQL database and there's a CLI to it. And then maybe they piggyback on the other mechanisms. So anyways, I think that this part of the design still really does matter though. It needs to be easy for developers to use, especially if they're interacting manually with it. Okay. Yeah. So cool, right on time. Developer experience is key. Yeah, it seems like the novel thing to do here is probably try to automatically come up with knobs based on some fancy heuristic. So yeah, overall, I really like this paper. We're at the end. So I will write a paper review about it, hopefully sometime soon. And thanks for joining. Don't forget to like and subscribe.